What's up, everybody? It's Dan from Sage Math Tutoring, and back with another video. This is for calculus problems for Calculus B, which is kind of like Calculus 2 in college, and a student of mine has to face these, so I want to make a video about them. So let's dive right in. Given that 1 over 1 minus x equals this summation with convergence in -1 to 1, find the power series for this. Okay. With center 0. So the concept that's required really for this is to understand the basic geometric series, which is this. Okay. And this equals this summation here. Okay. And this happens to converge when the R, which is the common ratio, is less than 1. Okay, so that's going to be important. So a simple example, perhaps, akin to this, is if we had something like 1 over 1 minus 2x, and this kind of matches the form 1 over 1 minus r, where the r in this case equals 2x, okay? And therefore, we could say that 1 over 1 minus 2x is really equal to this summation, okay? Where the r is right here. And it's really the case that this kind of substitution of the 2x into the r position is really fundamental to this type of problem, because once you've made it this far, you can go ahead and just kind of maybe rewrite it so that you apply that exponent to both of the factors. And you end up with 2 to the n, x to the n. Okay, so that's a simple example. Okay. However, it is the case that you would then have to acknowledge this information here, where the absolute value of r is less than 1. And what was the r? The r was this thing, right? Before we applied the exponent to both of the factors, the r was this. So you could kind of take that into account and just realize, okay, well, also it needs to be true that the absolute value of this needs to be less than 1 if we're identifying its interval of convergence, okay, which is another part of the problem. All right, and then you would just kind of take things from there. All right, namely, acknowledge that 2 will always be positive, so you're really looking at this. Divide both sides by 2, so we're really looking at that. Acknowledge that when you have the absolute value, it's going to be between the positive and negative versions of 1/2, and so on, right? So that is sort of like a simple case of this problem, right? So the bottom line is we have to acknowledge that this is indeed a geometric series pattern here, okay, where the 1 over 1 minus 9x to the 7th kind of sort of matches that 1 over 1 minus r thing, right? So in this case, of course, the r is, as everyone would guess, 9x to the 7th power. Therefore, we could replace r in the geometric series formula with 9x to the 7th, of course. So therefore, we could say that 1 over 1 minus 9x to the 7th is equal to the sum of the following terms, where the r happens to be this, right? At that point, keeping in mind that this is the r, we could do the same thing that we just did, in that we could apply the exponent across the board. So we therefore have 9 to the n, x to the 7th. I guess we could really say 7n. Hopefully my student watching recognizes that. And that would be what you could enter here. Okay, so this should go there. Pretty easy, right? So far. Identify the interval of convergence. The series is convergent from... Okay, so that's where, of course, taking advantage of this right here, we want this absolute value of this to be strictly less than 0. And therefore, we are looking at this. And dividing both sides by 9 would give us this. And then dropping the absolute value symbols would give us this. And taking the 7th root of everything would give us the following, right? And we have a negative here. So this negative could kind of go on the outside. So I'd rather represent it that way. Okay. So that is that. I guess we could clean it up even further by just saying, it's like 1 over the 7th root of 9, right? 1 over the 7th root of 9. Yeah, so this is kind of how you go about finding the interval of convergence. But the problem is, what you need to remember for my student watching is you find this nice interval here, and that's all well and good. But then you actually have to test these endpoints of that interval. So if we were to, let's see, test the left endpoint, which is negative 1 over the 7th root of 9. Let's kind of take a look at what would happen, right? I actually think that just paying attention really to this right here is the most important thing, because you could kind of pay attention to the sequence itself. If you were to substitute that into this, upon inspection, you would see that that would become a negative 1. Okay, there should be an n there. So that would be a negative 1 to the n. All right. Now what that means is when n is 0, the first term would be 1. When n is 1, the next term would be this. And there's just this sort of oscillation as you write the sequence or whatever. And, as n approaches infinity, this is not getting closer to 0. And whenever that's the case, it's the case that this, we could call that diverging. That does not converge, okay? So since we know that upon plugging in this endpoint into this, we end up with a divergence, we know that this endpoint is not included, okay, when it comes to, the interval of convergence, okay? At that endpoint, there's no convergence. Now, of course, we should be plugging in the right endpoint also. So let me just kind of set it up for us. And the right endpoint is right here. And if you were to plug that in, you would end up with, upon inspection, just positive 1, right? Now, once again, if you were to list this as a sequence, that would just be 1, 1, 1, 1, and that does not approach 0 either, okay? So therefore that diverges. So the endpoints are not included. Okay. So the series is convergent from, left end included, yes or no? Okay, so the series is convergent from -1 over, I'll just say 9 to the 1/7, to positive 1 over 9 to the 1/7, but the left end is not included and the right end is not included. So that is how you do that one. All right, so this one is very similar to the last one in that they give you the structure here, convergence in -1 to 1. Find the power series for this with center 0. What should stand out is that now there's an x on the top. Now there wasn't that in the previous problem. There was a 1 on the top. And remember, we kind of want this thing to match this thing. But the good news is you can kind of take the x off to the side temporarily here. Okay. And then just kind of treat the yellow part, okay, in such a way that you would match it with this. Okay, now we have 9x to the 5th is obviously our stand-in for that. So, we could be like, okay, cool, let's just rewrite it so that it's x. And it's the summation, right? N equals 0 all the way to infinity. In this case, it would be this to the n power, 9x to the 5th, right? And I'll keep that in yellow, actually. Pretty easy, I think, right? So, yeah. And then what could we do with that? Well, then, I guess you could, because they want this to be written, they don't have an x to the left, so we should probably bring the x back in now, right? We temporarily took the x out, from here to there, and then we did this little conversion with the summation notation, but now we got to bring the x back in. So what happens when you do that? So this would become, let's leave it out for now. I'm going to go ahead and apply this right now, though. So we have 9 to the n, x to the 5n. And then multiplying everything by x now. Hopefully my student watching recognizes that this is going to be 9 and x to the 5n plus 1. Okay, so for my student watching, just recognize, isn't it true that if you multiply this x times that would be x to the 5n times yet another x, and that would indeed become x to the 5n plus 1. So that should be the first entry right here. Okay, so we have this. Okay, identify its interval of convergence. Same deal as before, right? Whenever you're doing that, I would say always use this. Okay, so it's really that yellow 9x to the 5th that's going to be in the absolute value brackets, and we want that to be less than 1 because, the absolute value of r is less than 1. That's what we want. So let's see. Of course, the 9 is always positive. We could divide both sides by 9 and drop the absolute value symbols. And I think we all see where this is going. 5th root of everything. That's going to be, I'll just say 9 to the 1/5 down there, and 9 to the 1/5 down there. And testing each of those endpoints into the structure, right? So if you were to substitute the left endpoint here, that would give you a -1. And similar to the last problem, you'd have that oscillation, right? -1, +1, -1, +1. And that's a problem. Even if you brought the x in, let's say the x wasn't on the outside and the x was inside, which, you could think of it that way, then that would still be +x, -x, +x, -x, right? So the left endpoint is not included, okay? If you were to plug the right endpoint in, that would just be a 1, similar to the last problem, right? So that would just be, even if the x was in there, that would be x plus x plus x plus x, and that does not converge to 0 either, right? The sequence doesn't converge to 0. So therefore, this endpoint is also not included. Okay, so that is how to go about this one. So I'm assuming this information here should go there. This is the left endpoint, which is -1/9 to the 1/5. This is the right endpoint, which is +1/9 to the 1/5. And this is no, and this is no. All right, given this with convergence of that, find the power series for this with center 2. So this one's different because now the center is not 0. The previous problems were centered at 0, and when a series is centered at 0, as we saw from the previous problems, we use this. If a series is centered at 2, we want to use this, okay? And also, for example, if a series was centered at -3, we would have to use something like this, okay? Now, we still need to kind of flesh this out. We need to create a scenario that could compare with this. Let's see. Well, you have this x here, right? We want to kind of force a situation where x minus 2, which is sort of the thing that we need because it's centered at 2. We need to kind of force a situation where that's represented. So x is equal to x minus 2 plus 2, right? Isn't that the case? So hopefully we're acknowledging that any time you see an x, well, you could just replace it with this thing. So what if we did that? What if we said, okay, 1/7 minus x, sure, but that's really equal to 1/7 minus this bracket of, x minus 2 plus 2. I feel like that could be good. 7 minus x minus 2 minus 2, right, after distributing. Notice how I'm sort of preserving the x minus 2 in parentheses here. What would that be? 5 minus x minus 2. Right. And then you could factor out a 5 on the bottom. Okay, so that would be sort of like a 1/5 off to the side. And what would that result in? That would result in 1/1 minus this interesting thing here, right? Okay. So now we're ready to compare to this. So it's the case that 1/7 minus x is going to be equal to the following structure. we could leave the 1/5 outside. It would be equal to this raised to the n, x minus 2 over 5, right? Okay. Yeah, there we go. So once again, we have sort of the r represented here. And, much like the previous problems, we want to fill this part out here. This part needs to be filled out. And they probably want us to apply this exponent inside and maybe even apply this 1/5 as well. So therefore, if you were to do that, let's put the 1/5 on the inside, at least for now. We'll do this step by step. We hopefully can see that it would be x minus 2 to the n all over 5 to the n. And that's going to equal x minus 2 to the n, and then we have 5 to the n plus 1. Hopefully my student watching remembers, why that would be from the previous problem. And that would be a good candidate to enter into the answer box right here. Okay. Now, once again, when we're identifying the interval of convergence, it's probably best to rely on this. We are going to want it to be such that x minus 2 over 5 in absolute value brackets is less than 1. I suppose you could take out a 1/5 from that, right? And then you would have this. Multiply everything by 5. Do the thing. Add 2. 7. Negative 3. Okay, I think we're probably on the right track. So we already know you'd have a negative 3 here and a 7 here. Is the left endpoint included? Well, let's see. When you plug in negative 3, here, that would be a negative 5 over 5, which is just a negative 1. So that would become, and if you also multiply the 1/5 in there, so that would become a positive 1/5, negative 1/5, positive 1/5, negative 1/5, positive 1/5, negative 1/5. So yeah, that would not work, right? If you were to plug in this endpoint into this structure, that would be 7 minus 2 over 5, which is 5 over 5. So that would just be a 1. And then you'd have a 1/5 times that. So that would just be 1/5 and then 1/5 and then 1/5. That also is a sequence that would not converge to 0. So therefore it diverges. So therefore this endpoint is not included either. So we have negative 3, 7 as your endpoints. Negative 3, 7, and this is no, and this is no. Hopefully that makes sense. Okay. Differentiate the given series expansion of f term by term to obtain the corresponding series expansion for the derivative of f. Okay, so they're saying f of x equals this, but by the way, that also equals this. And we want to know what f prime of this is. So these are not bad. The concept involved is as follows. So if you have this, okay, a sub n x to the n, what, for my student watching, you need to remember is that you can just kind of very straightforwardly take the derivative of this by taking the derivative term by term. Okay, now, the first thing to note, though, when we're doing this sigma notation, you see how it starts at 0 here and starts at 0. When you take the derivative of this, okay, you then are starting at 1. Now, when we're in person, next time we meet, I could kind of explain why that is. It's not hard to see if you were to actually write out the summation and what would happen if you took the derivative and all that. But that's beyond the scope of the video. I'd rather just ask you to remember that when you take this and take the derivative of it, we're now starting at 1. Okay. And, this is the coefficient. A sub n is the coefficient, right? And what would we do if we were doing the derivative? We would put the n out front, right? So that's an n times the a sub n that is still there. And that's x to the n minus 1, right? Isn't that what we do when we take the derivative? So that's really all we're doing, actually, with this. Okay. I think the tricky thing is, though, that you want to make sure you're properly identifying the coefficient of this. Okay. Now, the coefficient is this, right? Because here's the x part. So this is like the coefficient part. So let's go ahead and just cut to the chase, right? We're now starting at 1. We bring the n out front. And then we have x to the n minus 1. Is there anything else we need to do with that? No, I don't think there is anything else we need to do with that. There's nothing we could do to simplify that, right? So yes, this would be the answer. So it's actually pretty easy. Okay, integrate the given series expansion of f term by term from 0 to x to obtain the corresponding series expansion for the indefinite integral of f. Okay. Well, yeah, so this is not bad either. I would say the integral is maybe even slightly easier than the derivative that we did in the last problem because the good news is we don't need to remember anything. We're not going to change the n equals 0 part. And it's sort of similar in that we're just doing the integral term by term here. So the concept involved is such that it would be f of x equals n equals 0 all the way to infinity, a sub n, x to the n, where, a sub n is maybe some constant that's out front. If you were to do the integral, you could say from 0 to x, it would be this. Okay, notice how it's still n equals 0 down here, which is nice. And we have just the power rule, where you add 1 to the numerator and then take the new, or add 1 to the exponent rather, and then take the new exponent and put it down below. So it's really just as simple as that. And that's nothing that my student watching isn't used to by now. So yeah, it's going to be as straightforward as that. So if we're looking at this, and we wanted to take the integral of that, I think my student watching would acknowledge that this sort of is the coefficient part, right? So that could all go out front, right? So we have -1 raised to the n, and then you have 4, but then you have this integral situation where it's, let's see, 0, x, and what would that be? Instead of x to the 4n plus 3, you should replace it with a t. So it's t raised to the 4n plus 3, and that's dt. Okay, yeah. So that's the way to handle this. And then you would just take the integral of that. So we end up with -1 to the n, 4, and that would be t to the 4n plus an extra 1 on top of that 3. So it would be this. This is the denominator down here. And it's going from 0 to x. Now, keeping that coefficient out front, we'll put the 4 out front this time. You would substitute x in there, right? in for t. So we would have x to the 4n plus 4 all over 4n plus 4 minus 0 to the 4n plus 4 all over 4n plus 4. Now, I think my student watching acknowledges that this would just be gone, and that should be an n. So we have 4 to the negative 1 n, and then you have this, right? And maybe simplifying a bit further by just multiplying across the top there. And then it's the case that we could factor out a 4 down below. So that would result in 4 times n plus 1. And you have this. These would cancel. And then you have this, right? So you have negative 1 raised to the n, x raised to the 4n plus 4 all over n plus 1. Right, but it's going to be the summation of that, right? Let's see. So therefore, in this case, we could say that it's going to be the following: f of t dt is really equal to this summation from 0 to infinity of this guy. Okay, so that is something that could go into the box. All right, so that's how you handle these. Okay, evaluate the power series expansion to show that ln of 2 is the sum of the alternating harmonic series. Right, so the alternating harmonic series in general, for my student watching, could be represented as following, where we have negative 1 and plus 1 all over n. And that's going to equal 1 minus 1/2 plus 1 over 3 minus 1/4 plus 1/5 minus, and so on. Okay. So it goes from positive, negative, positive, negative, positive, negative. And notice how you could say that there's this invisible yellow 1 under here, and the denominators go from 1, 2, 3, 4, 5, and so on. So that is true. And it's also the case that at some point it's taught that that equals ln of 2. Okay, now I think we can see that's specifically what they're asking about. They want us to evaluate this at x equals 1, which would be to turn this into ln of 2, right? And show that this is indeed the sum of the alternating harmonic series. So, interesting request. Not hard though, right? Because we can just kind of go ahead and substitute 1 in for x, right? And that would end up being ln of 2. And focusing on this, that would end up being when x is 1, you'd have negative 1, 1 minus 1, 1 to the 1 all over 1 as your first term. And I think we could see that that would literally just be a positive 1, right? I just kind of wanted to demonstrate how that would work. Then it would be, minus 1 to the second power over 2, right? Now that minus comes from this part because it's negative 1 raised to the first power in this case. And then, of course, we're putting 1 in for x. In this case, the n is 2. So we have that. And sure enough, you would see that this would pan out to be exactly what they're looking for, right? So I'm not exactly sure how much the teacher wants you to say about that, other than just kind of seeing quickly that this would be true. So that is true. Let's see. Use the alternating series test to determine how many terms of the sum are needed to estimate ln of 2 accurate to within 0.001. So this is where you need to be clear about the error situation, and that is the following. So for my student watching, this is a decent thing to remember. Now, all this is saying is if you add up a whole bunch of terms, the error, this is the error, it's the actual sum of infinite terms minus the sum up to a particular number of terms. And this is the error here. The error after stopping at this amount of terms is no larger than the size of the first term that you omitted. Okay. Now, what might that look like as a concrete example? Imagine your sum was 1 minus 1/2 plus 1/3 minus 1/4, and so on. And you decided to just stop after these 4 terms. Now, what that means is that n equals 4, capital N. Okay, so we have capital N here. So this is the first 4 terms right here. And what we know for sure is that the error of stopping at just these first 4 terms will always be at most this one, which is the next term. Okay, so I'll say that again. The error associated with adding these 4 terms will always be at most 1/5. It will be at most the size of the next term. Now, for my student watching, in case you're not clear, what is the error? Well, the error is what you take when you actually add infinite numbers in the series, and then you subtract the sum that you get when you only add a finite amount of numbers. And that difference is the error, right? And once again, the error associated with this amount of terms will always be at most, in this case, 1/5. Okay, the size of the 5th term. That's all this means. Great. So, with that said, hopefully with the concrete understanding sort of under our belt, let's see. We can remind ourselves of the series that we're dealing with, which is this, right? Because we already established that ln of 2 equals this, right? So we could say that the positive part of the nth term, the positive part of the nth term is this. Let's just call it b, right? Because we have a b here. So b sub n is 1 over n, right? These are all of the form 1 over n, right? So that should be pretty clear. Now, imagine you use the first n terms, okay? So imagine we use the first capital N terms. Well, the next omitted term, okay, the next omitted term would be, it really b sub n plus 1.
and that's 1 over n plus 1. What do I mean by the next omitted term? I mean this guy. If you go up to this, the next omitted term would be this, right? If capital N equals 4, the next omitted term would be this. So the next omitted term could be represented by this structure. Now think about it. Isn't that true of 1/5? You know, if we have a capital N of 4, then the next omitted term, which is b sub capital N plus 1, is going to be 1 over 4 plus 1. Doesn't that make sense? Okay. That's what's happening with these denominators. With every term, the denominator increases by 1. Okay. So that's true. And we know that whatever the error is, okay, whatever the error is, which you could say is this thing, the error has to be less than or equal to, according to the rule, less than or equal to b sub capital N plus 1, right? It has to be less than or equal to this thing, okay? So that's just the case, right? So we want the approximation to have an error less than 0.001. Isn't that the case? We want it to be accurate within 0.001. So therefore, we want the approximation to have an error that's less than 0.001. Okay. So at most, the error is going to be 1 over capital N plus 1. So we need this thing. Okay. We have to assume the largest possible error associated here and sort of guarantee that that is going to be less than 0.001. Okay. And that's going to be the ticket to the answer. Okay. So what we're going to do is we're going to literally solve this inequality, and that should show us what the answer is going to be. Now, one way of solving the inequality is we have 1 over capital N plus 1 is less than, now 0.001 is really 1 over 1,000. Okay. Yeah, I mean, cross multiplying. Should we cross multiply? I mean, we could just, yeah, we should cross multiply. So it would be 1,000 is less than n plus 1. And therefore, n has to be greater than 999, right? Now, we don't want to make the mistake of saying that n could be 999, right? N has to be greater than 999. So we want to know how many terms of the sum are needed to be accurate within 0.001. Well, we need 1,000 or more, okay? The moment we have 1,000 terms, then we can sort of guarantee that we're accurate within 0.001. All right. Now, that one's kind of a little crazy to explain. For my student watching, just sort of, rewind this, get clear on it if need be. This move might be sort of interesting, right? Making this green box acknowledgement, which is based off of this information. Okay. And then from there, making this jump where we need to realize that the largest possible error is this, right? If, generally speaking, right? And we need this thing to be less than 0.001. Okay. And we don't need to worry about absolute values because the capital N will always be positive. So, and then solving the inequality, little cross multiplication action. And then the trap is to think that the answer is 999 when it really needs to be greater than that. And other than that, it's just a matter of understanding, the concept. Okay, so this one is similar to the last one in the sense that we're going to use the same concept that has to do with error. However, this time we have this sort of integral situation. So let's dive into it. F of x equals this summation to determine this to within 0.0001. It will be necessary to add the first how many terms. Okay. So what you're going to want to do in this case is go ahead and take the integral of this, right? And we had already actually talked about that, where if you were going to take the integral, you could integrate term by term. So let me just back up a little bit. I'll just say that this is true because they told us that's true. It's, however, the case that to do the integral, that's going to be like this, right? It's going to be, you could take this part out, right? So you have the 3 to the n all over n factorial, and it's going to be the integral of this. So we have that. And in this case, I think we understand we are going to have this part. And this is going to be in its little box. And power rule applies. Goes from 6.9 to 7. Now, one thing that could sort of make our lives easier is to acknowledge that this n plus 1 can be treated like a constant, right? Because x is the variable we're focused on. So that n plus 1 could also be taken out, right? So on the outside, you have this, and then this is what's in the box. 6.9 to 7. Okay, I think we can see that if you were to plug 7 in for x, that would become a 0. So that's kind of nice. So that's a 0 minus whatever you get when you plug 6.9 in. So if you were to plug 6.9 in, you would end up with negative 0.1 to the n plus 1 still, right? Okay. Let me kind of rewrite that as follows for now. I want to be really careful with this because there might be a temptation to just be like, oh, double negative, so it's a positive. But remember, we have this exponent up here, and PEMDAS would have us apply exponents first. So there's this kind of oscillation happening here between positive and negative. So what I would like to do is just analyze this box off to the side, and let's really focus on that. Now, the reason I'm kind of doing this is because my goal, like I'm perceiving that there's going to be this oscillation between positive and negative taking place in the series. And that's because we have sort of a negative that's being raised to a power. And what my goal right now is to, in a sense, force a scenario where there's a negative 1 raised to the something, because that's typically how that oscillation is represented. And it's going to be multiplied times something else. So I kind of want to morph this into something that looks like that. how could we do that? Well, I mean, it's certainly true that this could be rewritten as negative 0.1 to the n times yet another negative 0.1. This green part, I don't know if I'm doing this in a stupid way, but that green part could certainly be understood to be a negative 1 times a positive 0.1 in there, raised to the n. We have still this, which, we could simplify, and the reason I'm doing this is because this would be a way of just sort of cementing that negative 1 to the n, which is kind of what I want. So I'm going to keep going. So we have negative 1 to the n times a 0.1 to the n times the rest of it. And then I'm sure everyone watching can see that that negative times this negative would turn that into a positive 0.1. So therefore, we have a negative 1 to the m, a 0.1 to the n, times a positive 0.1. And then I'm hoping we can all see that the bases are the same here. We have the invisible 1 hovered above the 0.1, and we could sort of consolidate that. Therefore, we have negative 1 to the n, and I'll just use blue for this. It's going to be 0.1 raised to the n plus 1. Okay, so the moral of the story here is that this thing really equals that. And once again, I have just made it so that it's along these lines where we have this character here. I'd rather have that character. So this goes here. So I'll just put it there. Okay. And consolidating that further would be, 3 to the n, negative 1 to the n, 0.1 to the n plus 1 all across the top, n factorial n plus 1. Okay. So it's possible you might not like the n plus 1. It might be nicer, it might be neater to rewrite everything so that it's just an exponent of n. So it can benefit us to remember that this right here could be rewritten such that there's just this additional 0.1 off to the side where this becomes this whole situation. And then you could recognize that these two have the same exponent. And you could rewrite everything such that you kind of consolidate those. Let's put this 0.1 out front. Not that it needs to be, but we'll do that. And then we have negative 1 n. And with regards to the two yellow things, that's 0.3 to the n. And that's still all over this. Okay. Great. And what are we doing? We are determining this to within 0.001. It will be necessary to add the first how many terms in the series. Yes, so please remember the adding the terms, and the error will always be greater than or equal to the omitted term. So we actually need that omitted term to be less than that. Okay, hopefully that rings a bell. and then we'll have an idea about how many terms we need to add. Okay. Now, they told us that we can use technology in a table to solve this. So I went ahead and used Desmos with this. Okay. Now, there are multiple ways of doing it. TI-84, you could essentially just plot this on your Y line and make a table out of it. Okay. Now, I want to be very clear though, I replaced all the n's with x just for the sake of entering it into Desmos. Now, in Desmos, I chose to use a function where it's like f of x equals this thing. All right. Because I knew that on the next line, I could just say f of 0, f of 1, f of 2, and so on. So let's take a look here. F of 0 is 0.1. So you could imagine that when n is 0, the first term present in the series is 0.1. The next term is negative 0.015, right? The next term is positive 0.0015. The next one is negative, what is that? 0.0001125. And then the next one is, of course, this one. Now, you don't have to write it out necessarily. I think just by looking at your calculator, it should be fine. So that's 50675. 1, 2, 3, 4, 5, 6, 7, 5. And that's adding. So, you know, we want the error to be less than 0001. Okay, the error needs to be less than this. And the only time where we get a number that's actually where the magnitude of it, the absolute value of it, we don't take into account the negative. The only time we get an absolute value or a magnitude that's actually less than this is not here, right? Because the magnitude of this is greater. But this is the moment where we can be sure that, like this number is less than that. So therefore, if you add the first, what is this, 4 terms, it will be guaranteed that the error is going to be less than this. Okay. So for my student watching, hopefully that makes sense. That's a way of going about it. All right. Once again, in the TI-84, there's a way to just enter this on your line and then make a table, and then you could see these. But it's up to you to recognize that, imagine adding these and setting them up like that. And this is your ticket to victory because this is the first number that's less. And again, this ties into the concept that we did in the last problem, right? So, great. Now you would need 4 terms. And then they say they want you to actually approximate that. Okay. Enter the answer accurate to 4 decimal places. So that will be a matter of literally adding those terms, right? So if you were to add all 4 of these in your calculator, you would get, my calculator is showing 0.08638875. But if we're going to do it to 4 decimal places, that's 0.0864. All right, so that's how you do that one. Okay, we know that this is equal to that, which converges to that for t values in the interval from -1 to 1. Okay, got it. Compute the definite integral from 0 to x of this. Okay, so for my student watching, when you perform the integral, at some point you're going to be substituting x in for t, right? This one is really not that bad because hopefully you remember, if you compute this definite integral, I mean, it's really just the power rule across the board, and you'd be replacing t with x. So hopefully my student watching would agree that's just going to become x, and then the next one's going to be negative, so it does say plus here. So I'm going to put in negative. So I have negative x cubed over 3 plus x to the 5th over 5. And this is minus x to the 7th over 7. And this would be positive x to the 9 over 9. So that's not a big deal, right? Okay, write the series compactly using summation notation if the series alternates include the alternator separately. So the alternator is going to be a -1 to the n thing. So I'm wondering if that's their way of saying don't write -1 to the n in the box. Okay, even if, your answer includes -1 to the n, maybe we should not write -1 to the n in the box. So that's one thing to think about. So how can we write the series compactly using summation notation, meaning this series that we just made? Well, that would be a matter of, doing the integral of this thing, I think, right? We could acknowledge that the original general term is this, and we could integrate that, from 0 to x. So cool. And it's the case that -1 could kind of go on the outside. And we have t to the 2n, dt in this case. And I think my student watching would agree. We have -1 to the n, and we have our brackets. And that's really going to be t to the 2n plus 1 all over that new exponent, which is 2n plus 1 down here. And then we have from 0 to x. We can already see that when we substitute 0 in for t, that's going to become a 0. So we only really need to pay attention to that. So we have -1 to the n, x to the 2n plus 1 all over 2n plus 1. So therefore, this could be rewritten as this summation, where you have this -1, which I guess would be the alternator. And then you have your x to the 2n plus 1 all over 2n plus 1. But once again, they said include the alternator separately. So I'm wondering if really we're just putting this in there. Okay, great. Find the interval of convergence for the new series. Well, the old interval of convergence was this, from -1 to 1. Notice how -1's not included in the interval because it has parentheses next to it. And notice how this also has parentheses next to it. So when you do a term by term integration, it should keep the same radius of convergence. Now let's remember the radius of convergence. You have 1 over here, you have -1. The radius is the distance from the center to the endpoint. So when you perform term by term integration on this original scenario, you will always keep the same radius of convergence. However, after integrating, this is what the professor is testing you on. After integrating, you need to test these endpoints again. Okay. Because even though the endpoints were not included in the interval of convergence for the original situation, the endpoints might actually be included in the interval of convergence for this integrated version. Okay. So, really, our ticket is going to be this, right? So, let me put that off to the side. And let's test the left endpoint, which is -1. So, testing x equals -1. Rewriting -1 to the n, -1 to the 2n plus 1, all over 2n plus 1. I'd rather think of that as -1 to the n times -1 to the 2n times yet another -1. That is -1 to the n. Now, this is a -1 raised to an even number. Anytime you have -1 raised to an even exponent, it's going to just be a positive one. So I'll write that. Then we have a -1 here. So we have 2n plus 1. So you have this blue thing, and this yellow thing. I'm going to put both of them off to the side. And over here, I will have this. Now, this is going to be positive or negative depending on whatever n is. And this is going to make it this the opposite sign. Okay. So if this becomes a positive 1, when you multiply this positive 1 times a -1, it's just going to become a -1. If this becomes a -1, when you multiply that -1 times this -1, it's going to become a positive 1. So it's almost as though this whole thing is kind of like the alternator, you know? Now, my thought here is we could do the alternating series test on this, which really has two conditions. The first condition is it the case that the positive part, which is this part, is it the case that the positive part is decreasing as n gets larger? Well, I think my student watching can see that the answer is yes, because as n gets larger, the denominator is getting larger, and that makes this entire number smaller, right? So that's the first condition of the alternating series test, and we just satisfied it. We know that the positive part, regardless of the alternating part, the positive part is decreasing. So that condition is satisfied. Now, the second condition is that the terms need to approach 0. And that is most definitely happening for the exact same reason that I just said. Okay, so not only is this decreasing, but it's not only decreasing, but this whole thing is approaching 0 because as n approaches infinity, it's almost as though you could substitute the entire denominator for infinity, and 1 over infinity is essentially 0. Okay, so therefore, both conditions of the alternating series test are satisfied. And also, you would use the alternating series test when you have this alternator here out front. That's kind of the reason why I'm even choosing to do that. Okay. So, yeah, by the alternating series test, the signs alternate, the magnitudes decrease, meaning the positive part decreases, and approach 0, which is the third criteria. So, the left endpoint, therefore, is included, right? The left endpoint of -1, where's that? Right here, is included. So now we need to test the right endpoint, and we will be testing it when it comes to this, right? So we are now testing x equals 1, and that would be -1 to the n. We have 1 to the 2n plus 1 all over 2n plus 1. Well, I have a feeling this can be a very similar situation. Let's take into account that we have that alternator. In this case, it's going to be 1, 1, because 1 to the anything is just 1, right? So actually, it's just 1. So then we have that over 2n plus 1. If you want, you could kind of wrap that in brackets. Consider this part the alternating part. And once again, by the alternating series test, this actually converges because once again, we have this alternating part. It's the case that we have the first condition, which is that the later terms are smaller than the earlier terms. So, for example, if you were to think of the second term, that would be smaller than the first term, and so on. So these are decreasing as n gets larger. And not only that, but this whole thing is approaching 0 as n gets larger and n approaches infinity. So this also converges. Therefore, the interval of convergence is most definitely -1 to +1. But I think what the professor wants is for you to notice that the interval of convergence for the first thing had parentheses, and the interval of convergence after performing the integral term by term, we get brackets here. Okay. Okay, what common function does this series represent on its interval of convergence? So that's tricky because you look at this and you're like, I don't know, you know. But we know that if you take the derivative of this, you end up getting this. Okay. Now, what does that remind you of? It's like the derivative of something gives you that. And the trick is to recognize that the derivative of arctan of x would indeed give you, well, really 1 over 1 plus x squared, right? Now this says 1 over 1 plus t squared, but to be sort of precise with that, we could say that the derivative as 0 approaches x of this, right, dt, that is going to equal arc tan of t, from 0 to x. Okay. Now, when you substitute 0 in for t here, upon reflection, you would recognize that the arctan of 0 is just 0. So therefore, this becomes arctan of x. So we could say that what we've learned is that arctan of x actually equals this thing. Okay. So that's what we've learned. And we did that by, remember, taking the integral of these, right? And then we ended up with that. And it turns out that that happens to be the same as arctan. Okay. So great. Arctan of x should go there, and that should be fine. Okay, so that's how you do these. Hopefully this was helpful, and I will see you all later.